Hello, in this lecture we are going to do a problem that was asked in JEST examination 2015, and as we are doing now electrostatics, so it is based on electrostatics only, and this particular problem is based on a potential which is called as Yukawa potential and sometimes also referred to as a screened Coulomb potential. So it is also referred to as screened Coulomb potential or Yukawa potential. Okay. And this question was asked in your JEST examination. And let us see how to do this question. So the question says the electrostatic potential due to charge distribution is given by Vr is equals to A e की power minus lambda r divided by r, where A and lambda are some positive constants, and then the total charge enclosed within the sphere of radius 1 by lambda is given by option number A, B, C, and D. All of these options are given to you. Okay. Now, in order to do such problems, one must be aware that this particular problem we have done for the most general case in a previous particular lecture also. But this particular question was again asked for a specific case where your radius now is specified. Instead of asking total charge enclosed by the system, now it is asking what will be the total charge enclosed within the sphere of radius 1 by lambda. So let us do this particular problem in detail. Okay. Now, while doing this particular problem, the first thing that you should do is there are two ways. The first way can be to do del square V and then try to find del square V and then try to find rho upon epsilon naught. And from rho, you just take your integration with respect to volume and get back your total charge enclosed. Or another way can be to use Gauss law. Another way can be to use the Gauss law. So there are two ways. I'll go with the second way because that seems to be more uh, appropriate here, and I will let you know why I'm doing that. Okay, so why I'm doing that, also I'll let you know. Okay, so let us start. Okay, so let us start with it. So what I would do, I have two things to do. The first thing is, this is sometimes called as, again I've told it, this is sometimes called as screened Coulomb potential, or at times also referred to as Yukawa potential. This is just for information. I'm referring you a slight information. Okay, and it arises in this particular potential arises in like semiconductor systems where the interaction takes place in a medium where interaction between the charges, you can say, takes place in a medium which is you can say that it is dielectric, in a dielectric medium. And this dielectric medium, what does it do? It partially which which partially you can say screens the Coulomb interaction between the charges. Coulomb's interaction between the charges. And such screening potential is given by this Coulomb's interaction between the charges. Okay, so slightly a little bit about this particular potential. This is quite many examinations has been asked. Now, how to go about it problem? Now, there are two ways to go about it. The first way, the very simple way, is to simply enclose it. So this is your let's say this is your system in which you have this row. You have some row. I'm just making it. It's just not that way. I'm just trying to say that this particular row or charge distribution gives rise to potential given by what is the potential? Br is equals to A e की power minus lambda r upon lambda. So let's say this is the potential which has been given to you. The first strategy can be to find the flux. So net flux through the sphere of radius given, I think it is given 1 by lambda, of radius 1 by lambda will be equal to net charge enclosed net charge enclosed divided by epsilon naught. So this net charge enclosed will be inside the sphere of radius 1 by lambda. So this will give you answer. So first way can be to do this. So let us do that thing first. So I think this is an easier approach. So I'll do this particular thing at first. So my electric field can be written as minus of grad of V, and that will be, I think, minus of del by del R of your this thing A e की power minus lambda R upon R, and then you have this R cap. So what I would get is minus A, and then you have this derivative will be minus lambda e की power minus lambda R upon R, and then you will have minus A e की power minus lambda R upon R square, and then you will have R cap. Sorry, you will have an R cap. So overall, my electric field is in radial direction given by A. Sorry, this will not be here. This will not be here. Sorry. Okay, so A, and this will be, I think, lambda e की power minus lambda R divided by R plus e की power minus lambda R divided by R square. Or in other words, I can write A 1 plus lambda R divided by R square e की power minus lambda. I think this is clear to you. So this is how my electric field I can write as a function of R along R cap direction. So electric field seems to be spherically symmetric function. So it is clearly a spherically symmetric function. It's not dependent on theta and phi. Anyway, okay. Now let us further move and try to find the flux due to this electric field uh, within a sphere of radius 1 by lambda. So this will be E dot ds, and I will write R, and then I will write R as 1 by lambda over this particular sphere of radius R equals 1 upon lambda. This will give you net charge enclosed divided by epsilon naught, and which will give you net charge enclosed divided by epsilon naught, and that will be integral A 1 plus lambda R e की power minus lambda R, this R cap dot R cap. So this is R cap dot R square sine theta d theta d phi R cap. So on the surface, the area element patch is given by R square sine theta d phi R cap. So this is the patch on the sphere, and that particular patch on the surface has this differential element ds given by R square sine theta d phi, and this will give you, this particular expression will give you net charge enclosed. So this R, sorry, there is an R square here also, so that it will get cancelled. So overall, this particular integration will come out as, summation q upon epsilon naught is equals to A into 1 plus lambda R e की power minus lambda R, then sine theta d phi will give you 4 pi. It will give you 4 pi. And all of these things we are evaluating at R equals to 1 by lambda. See here, you do not have any dr term. So basically R is a constant here, so you can take R outside. Okay, so overall, net charge enclosed by the system divided by epsilon naught is given by a e की power minus lambda, and all those things. So you just place A into 2, it will become, and it will become e की power minus 1, and here you will have this 4 pi. So overall, this entire term, net charge enclosed, can be written as 8 pi epsilon naught A upon E. So this is the net charge enclosed by the system, net charge enclosed within a sphere of radius 1 by lambda, when your potential is given to be Yukawa potential. So whatever charge distribution generates such a potential, if we enclose that particular charge distribution within a sphere of radius 1 by lambda, I would get that total charge enclosed would be 8 pi epsilon naught A upon E. Okay, is that clear to you? I hope it is easier for you to follow. Okay. Another approach that we can take probably is approach number 2. We can first find, I have already found electric field, so I'll write electric field as it is. So my electric field comes out to be, what was electric field? Just give me a minute, I'll just copy it down so that things are not. So there is an electric field. Electric field is A, this. So electric field is given by 1 plus sorry, 1 plus lambda r divided by r square, and then you have e to the power minus lambda r cap. So what you can do, instead of doing all these things, one can do another thing, and that another thing is to write del dot e vector. So what will be del dot e vector? Let us write that of course. So del dot e vector is given by rho or epsilon naught, that will be equal to rho or epsilon naught is due to Gauss law. Okay, now let us first find del dot e vector. And I already cautioned you that whenever you have this r cap upon r square term, you have to be certainly cautious, because you know that del dot r cap upon r square is 4 pi Dirac cube of r. Sorry, is 4 pi Dirac cube of r. Okay, so if you write del dot e vector here, so your del dot e vector will come out as uh, del dot, and then you have 1 plus lambda r, and then you e to the power minus lambda r also in place, and you take r cap upon r square aside. You take r cap upon r square aside. Why I've taken r cap dot r square aside? So that this particular divergence of this particular thing will become 4 pi Dirac cube of r. So overall, I will write my del dot e vector is given by 1 plus lambda r e to the power minus lambda r, and then you have del dot r cap upon r square, and then plus r cap upon r square dot producted using the divergence of sorry, gradient of this, and gradient of this will be given by del r of, and again there is an r cap, just don't worry about it. So this will be 1 plus lambda r e to the power minus lambda. Okay, so overall this will give you there is some a somewhere, and I've forgotten what. I think there is a somewhere. So you just keep a like a is a constant. You just keep multiplying it with a. So I don't think this will be an issue otherwise. So del dot e vector will be you will get as 1 plus lambda r e to the power minus lambda r. This will be 4 pi a, and this will be Dirac cube of r. And then you have r cap dot r cap upon r square dot r cap. And what is del by del r? Del by del r will be, I think if you differentiate it first, this will be lambda e to the power minus lambda, and then minus derivative of this lambda e to the power minus lambda r, and you have 1 plus lambda r, and this is like a multiplied with a. So overall this will get cancelled. Overall this term will remain. So you will get plus, and there is a negative here. So this will be minus lambda square. This become lambda square, and there is one r also there. So one r will come below, and then there is a also. This is a here, and this will come as e to the power minus lambda. So if you write like this is minus lambda square r, and one r gets cancelled. So overall you will get this. I hope it is clear. And I think this is this particular thing, because Dirac cube r is situated at r equal to 0. So it will only be there if r is equal to 0, because if r is not equal to 0, this will be multiplied with 0. So forget about all these things. Just write 4 pi a Dirac cube of r. All these things I have discussed in a lecture separately. So I'm just doing it quite quickly. So this will be rho upon epsilon. Now, if you want to find the charge density, if you want to find the charge density, if you want to find charge which is enclosed within the sphere of radius 1 by lambda, so within 1 by lambda you can understand this particular thing, because r equal to 0 is inside this particular radius. So this particular thing, when integrated volume wise, volume over which is like which encloses the volume of a sphere of radius 1 by lambda, so it will come out as 4 pi a will come out, and this particular Dirac cube d tau will come as 1, and this is minus lambda square upon r a e to the power minus lambda r. This will be r square sin theta d phi dr. This is integration. This is the volume integral term, and this will be integrated from 0 to 1 by lambda. Okay, this will be integrated from 0 to 1 by lambda. This will give you total charge enclosed. Okay, and this has to be multiplied with epsilon naught, and this has to be multiplied with term epsilon naught, because rho upon epsilon naught, so epsilon naught has to be multiplied. This will give you rho, and rho when integrated with respect to volume will give you back the total charge enclosed. So total charge enclosed will be, this will give you q is equal to epsilon naught 4 pi a. I think this is 4 pi a. 4 pi a epsilon naught will come out from here, and this Dirac cube r d tau will become 1. And then you have this term minus lambda square is a constant, take it out. A is a constant, take it out. Epsilon naught is a constant, take it out. And you have this integration r. I think this is dr. Okay, if I'm not wrong, this is r dr. Oh, sorry, this is r, and then there you have dr, and this sine theta d theta d phi will give you, I think, 4 pi. This will give you 4 pi. I think, is that clear? And there is e to power minus lambda also. So I'll write e to power minus lambda also. Sorry. So overall, this will be the term. So sine theta d theta integrated over the entire square will give you 4 pi from here. I'll get 4 pi from here. And this particular radial term I'm writing. So lambda square I've taken out, a I've taken out, epsilon naught I've taken out, r and r will be here, r e to power minus lambda r, and this will be it. Now, if I if I go ahead, then if I write total charge enclosed will be 4 pi a epsilon naught minus lambda square a epsilon naught, and then what will be the value for this if I integrate from 0 to 1 upon lambda? Let me find. So if I integrate from 0 to 1 by lambda, what will I get? If I integrate, this will become as e to power minus lambda r upon minus lambda from 0 to 1 upon lambda, and then again plus lambda square a epsilon naught. I think 4 pi also will come. If I forgotten it, kindly write it here. So 4 pi will also come. And this particular thing, integration, r ka derivative is 1, e to power minus lambda r ka derivative integral will come as e to power minus lambda r upon minus lambda dr from 0 to 1 upon lambda. And again, if I do it all over again, so what I will get q is equals to 4 pi a epsilon naught minus 4 pi lambda square a epsilon naught, and I think this is negative, and again there's a negative, so overall this will become positive upon lambda will come. Okay, and upper limit if I place, I will get 1 upon lambda into e to power minus 1, and then minus in place of r, if I place 0, so it will come as 0 plus lambda square. And again, if I integrate it, what I would get? I would get lambda square a epsilon naught into 4 pi. And this particular thing again integrated will give you e to power minus lambda r divided by lambda square. And from where to where you have to integrate? You have to integrate from 0 to 1 upon lambda. Okay. So again, if I take the last integral, if I find what is the last, this bracket, I'm getting this particular, all these things are as it is, I'm copying it up. This will be lambda square, so this will be 4 pi a epsilon naught upon e, then this is 0, forget about it, plus this lambda square will cancel, and this 1 upon lambda, if I place, it will come as 4 pi a epsilon naught upon e, and if I place 0, so it will be minus 4 pi a epsilon naught. So both of these terms will get cancelled, and total charge enclosed will come out as 8 pi a epsilon naught upon e. So in any case, if you go with this lengthier approach or the shorter approach that I took initially, both of them will render you the same answer, will give you the same answer, that is 8 pi epsilon naught a upon e. So this was the solution for the JEST question 2015, and time and again I have observed in my experience that things like these are coming, for which I have done some electrostatic lecture also. I'm kindly requesting you to visit them, and if you find that there is certain discrepancies in having solved this particular problem, kindly let me know. Till then, take care.